From evening in Europe. I'm happy to start 2025 virtual lecture series, and we will have an energetic jump start of this presentation of Dr. Peter Knittel. So Peter studied chemistry at Ulm University and got his PhD in analytical chemistry. His highly interdisciplinary work developed expertise into a number of fields, including electrochemistry, qualitative and quantitative analysis, solid-state chemistry, semiconductors, biointerfaces. In 2017, Peter started working at the Fraunhofer Institute of Applied Solid-State Physics as project manager, taking over the work packages from European Union project and coordinating German project Photocon. As group manager at Fraunhofer, Peter overseeing various diamond activities. Also, as deputy head of the business unit Quantum Systems, Peter represents these activities at IAF in the context of quantum computing. His group focuses on CVD growth of synthetic diamond for quantum technologies based on nitrogen vacancy centers. Peter, the stage is yours.
Yeah, thank you very much, Olga, for that very nice introduction. I'll try to share my screen. So now you should be able to see the first slide. Is that correct?
Yeah, it's perfect.
Amazing. Yeah, then let's get started. So I'm quite happy to present the work that we're doing at Fraunhofer IF on diamond films for quantum technologies. This presentation shall give you a bit of an overview on our activities. I cannot talk about everything, but I will try to give a good overview. And if you're more interested in some details, there are also publications always cited on the slides. So first off, I want to give you just a quick glance on where I come from. So I work at Fraunhofer IF, Institute of Applied Solid-State Physics in Freiburg. Freiburg is located in Germany, very close to the border of France and Switzerland. So in this triangle between the countries. We are a Fraunhofer Institute, one of the oldest Fraunhofer Institutes, actually, I think the fifth that was founded in Germany in 1957, about 300 employees. We have a large clean room area and also MOCVD. So the MOCVD part is where we don't produce diamond, but where we actually do our second material or material class at Fraunhofer IF. That's 3-5 semiconductors. So we're basically working on these materials, diamond and 3-5 semiconductors. And this is done within 5 business units. One business unit focusing on high frequency electronics. Power electronics is one, optoelectronics that includes also quantum cascade lasers. And the ones that are of most relevance for this talk are the business unit 4 and 5, which deal with quantum sensing, basically quantum sensing also based on NV centers in diamond, and quantum systems that works on quantum computing, also from an algorithmic perspective, but also from a hardware perspective. So coming to the diamond synthesis, just a very brief overview. We have many activities here. We actually have 3 groups dealing with growth of diamond. One of these groups is mine, which is focusing more on thin layer growth. But on that side, we're working on doping of diamonds, so nitrogen for NV generation, boron doping to get conductive p-type diamonds, phosphorus doping to produce n-type diamonds. And in our clean room, we also do processing, so lithography, etching, metallization. We also have polishing and laser cutting tools to produce diamond in different shapes. So this is the overview. And now let's come to the outline of the talk today. So I will start very briefly with introducing just general why diamond should be, or why we are working with diamond and how it is deposited via chemical vapor deposition, just to get everybody on board, even if they are not familiar with that topic. Then we will dive directly into diamond for quantum technologies. And here there are a few topics that I will cover, which is color centers, how we create them in diamond, how we position color centers, and specifically how we can do this via growth. How can we control the spin baths surrounding the color centers, and then how these diamonds are used in quantum sensing applications, but also in quantum computing applications. And at the end, I will summarize. So diamond in general is known to most people because of its use as a gemstone, and probably some people will never know a lot more about it at this point. But then early on, when diamond was grown synthetically, people realized that it's a very good material for also conductive elements like electrodes. What you see here is a polydiamond plate that is boron doped, conductive diamond. Also in many technical applications, we nowadays make use of the high hardness. So we have the highest values for Vickers hardness and Young's modulus for all solid materials with diamond. And what you see here is basically a few forms of single crystalline diamonds. Historically, the first HPHT synthetically grown, so high pressure, high temperature grown diamond, which is was done in 1955, where the journey started on the technical side, and not before 1961. The first demonstration of CVD growth was done. But if you look on publications, you actually see that in the 70s, from the 70s to the 90s, there was not that much activity. But when CVD growth was established on a routine base, then we see a huge increase on publications showing the importance of this material on the scientific side. We see another jump in 1997, when especially the single defects were discovered that can be used for quantum technologies. So what is the reason why in this period in between there was quite a lot of activity? There are also some properties of diamond that should be mentioned here that are very outstanding, even though that hasn't a lot to do with the quantum applications. That's the diamond in electronic application. And I want to point out the high hole mobility that diamond has, and the high breakdown field that could be realized in a power device based on diamond. But what is nowadays also very often used is this very high thermal conductivity. And if you ever have the chance to visit us at Fraunhofer IF, and you wanna see how this thermal conductivity actually looks like in reality, we can do a cutting test with a diamond wafer, and you will realize that such a diamond wafer, using the heat that is transferred from your hands, cuts through an ice cube like a knife through butter. So that's very impressive, and maybe at some point you're able to see this. Right. But how do we grow diamond? Diamond, in principle, by if we grow it via CVD, we ignite a plasma. All of the systems are more or less similar constructed. So we have some kind of power source, which is in most cases a microwave. That is coupled to a resonator, where we excite a plasma. Inside this plasma, we have the constituents that we need, mainly carbon, obviously, but in addition, a lot of hydrogen. So forming radicals in the plasma of the CH radicals in the plasma, we can then build up diamond. The hydrogen actually is important in this approach because we are not in the conditions to grow diamond. We are at low pressures, so meaning at around 10 to 200, 300 millibars, so far away from natural conditions, and rather high temperatures, but even not as high as it is in nature when diamonds are formed. So the stable allotrope typically in these conditions is graphite. And to avoid forming graphite from the methane or from the precursors, we have to add hydrogen that readily etches this sp2 carbon, and that leaves us only with the diamond sp3 carbon. So this is the general principle. Nowadays, you can get these nice reactors from Seki diamond. We also have one of them, but in our institute, we actually designed our own machines that you can see here. So they have a very typical shape. This is this ellipsoidal shape or X shape, which has the advantage that the microwave that we couple into the resonator actually is coupled in via an antenna on the top part in the first focal point of this ellipse, and it refocuses in the bottom part where we also locate our samples. So, and we have two types. One is for smaller area, up to 3-inch area polycrystalline growth. We can obviously also grow single crystalline, but there are no 3-inch wafers available at that size. And larger machines, they can grow on an area of up to 6-inch. The machines are equipped with boron or boron precursors, 3-methyl boron mainly, phosphine for phosphorus doping, and nitrogen for n-type doping. Then we have one special type of reactor, or actually nowadays two, that allow us also to decouple the growth preparation steps in the machine from the substrate. So in the other machines, or in lots of other also commercially available machines, you always have the diamond in touch with your plasma from the point where you actually ignite the plasma till you end your process. Here we can equilibrate conditions. We can remove the diamond from the active plasma, stop the growth in such a way, and this gives us the chance to actually grow for very short periods of time. And we specifically made these actually to produce delta doped layers that you will see later on. So in these machines, we mainly use these small 3x3 or up to maybe 5 or 10 by 10 millimeter single crystalline diamonds. But there is one group specifically working on improving or increasing this size, which is the heteroepitaxial growth group from Vadim Lebedev at our institute. They are using a technology that was pioneered in Augsburg, and I saw that Matthias Schreck is in the audience. So they started working on this technique using silicon wafer that has a buffer layer consisting of yttrium stabilized zirconia and on top an iridium layer. With that, the lattice mismatch can be adapted, and you can use so-called bias enhanced nucleation to form oriented grains on a silicon wafer. With that, you're in principle not limited in size anymore. Even though the nucleation on a large wafer has some challenges. But this is the approach that is used. There is another company in Japan that makes use of a bit of a different structure, but the idea is always similar, using this bias enhanced nucleation, forming oriented grains. And with that, you can produce 100 oriented diamond wafers. I think from Diamond Foundry, that is, they recently shown that this can even lead to 4-inch diamond single crystalline wafers. We have also an active project that tries to achieve growth on 111 for 111 diamond wafers, which is a bit more challenging. But this is also possible. And it has some challenges. And you may ask why, if this is already possible, producing diamond wafers, why people don't use diamond wafers all the time. First off, you don't get them easily at the moment in this large size. You get small pieces, but the bigger backdraw is actually so this is just an image of a 2-inch wafer that we also have at IF. But coming to the problem that we see at the moment is that these heteroepitaxial diamond wafers have very high dislocation densities, so up to 10 to 8 per square centimeter. That means that most probably due to the merging of these oriented grains, you incorporate lots of dislocation defects and other crystalline defects into the wafer that makes them at the moment not usable, especially for electronic applications. For quantum applications, there is still maybe a chance that even at higher amounts of dislocations or crystalline defects, you may use them. But if you want to use the best material that is available, people still use these single crystalline wafers that are produced basically either by high pressure, high temperature growth or by CVD growth on these high pressure, high temperature substrates. Okay, so this is generally on how we grow diamond and what our activities are. So I hope you got a bit of an insight. So let's move on to why diamond is actually of interest in quantum technologies. And the reason is that the diamond matrix can contain a color center, being a nitrogen atom with an adjacent vacancy that bears an electron spin, and this spin can be easily addressed optically. In addition, just by optical pumping, we can initialize it in a spin state. So this is shown here in this plot. So if we shine green light on a diamond that contains NVs, we're actually actively pumping it into the MS0 state, because if it goes from the MS ±1 spin state into the excited state, it will overgo into system crossing to this non-radiative path and go back into an MS0 state instead of the MS ±1 state, and that allows us to initialize the diamond in this MS0 state. So this is quite cool, because if you think about it, even if you have like a gemstone diamond, and if you use a green laser pointer and you shine green laser light on it, you know that for sure that there are some NV color centers in it. You can prepare a quantum state on basically a gemstone without any additional lab equipment. But this is one feature, obviously, but why is this important? Because with that, it allows you to manipulate this. It allows you to manipulate the system coherently, and this is what you actually use for quantum sensing and quantum computing approaches. So if you make use of it in quantum sensing, you can, for example, measure magnetic fields. This MS ±1 state is degenerate, and as soon as you apply a magnetic field, it undergoes Zeeman splitting. This Zeeman splitting leads to this split in MS- and MS +1, and also due to this non-radiative path, you get, if you drive the NV center with a microwave, you get dips in your fluorescence, and depending on the distance between these dips, you can see how high the magnetic field is that the NV center feels. So this gives you a magnetic field measurement without any additional calibration. The emission of these NV centers is in the red. That's why also if you have a diamond that contains extremely high concentrations of NV centers, you will see that they have this nice reddish color, also visible down here in the polished diamond. But in addition to that, there are a few things that are of high importance. One thing is that this magnetic field splitting is completely independent from your diamond in principle. So you can do this measurement calibration free. It only depends on natural constants. You don't need a magnetic shielding because you can compensate for the Earth magnetic field. And the quantum state can be prepared for very long time, so up to 2.4 milliseconds have been shown. You can make use of the surrounding nuclear spins, for example 13C, that have an even longer spin coherence times of up to 60 seconds. And the spin dephasing is also extremely long for the diamond NV center. So all of these properties make it an ideal candidate for quantum technology applications. How do we get these NV centers into diamond? There is a straightforward approach that is that is used in many groups, especially if they want to create single centers. Here you can basically implant the nitrogen atom. With that, you already generate vacancies in the crystal lattice. You make these vacancies mobile by a thermal treatment afterwards, and with that, you end up having an NV center formed. So this is basically an easy approach that allows you to generate single NV centers. The backdraw is that you actually generate significant damage that can, again, decrease your coherence time, but especially decrease the stability, meaning the NV center actually that we use is in the negative charge state. If it discharges to a neutral state, we cannot make use of it anymore. And if we have charge traps in the diamond generated by this treatment, the NV will discharge to this NV0 state. So that's a bit of a disadvantage of this method. The other thing is that a thick layer with high concentrations of NV ensembles is very hard to achieve in this way. Also to have it homogeneously over a certain area. This is where the CVD growth comes into play. And you can easily incorporate nitrogen in diamond. So the incorporation efficiency is rather high, in the range of 10 to minus 4. And with that, you can produce NV densities in the ppm regime if you do a post-treatment. So here again, you see these nice red colored diamonds. These are some diamonds that contain NVs in the concentration of 1 ppm and above, but also lower levels can be achieved. And the spin coherence time of these diamonds is mainly determined by the surrounding substitutional nitrogen, which is also called P1 center. And this is shown in this plot here. So depending on the amount of P1 centers, you actually decrease your spin dephasing time. But what this actually shows is that there is a theoretical model developed in the Wolfsworth group that you can grow these diamonds and you reach the theoretical limits with this growth approach by CVD. So this is fine for some applications that require bulk diamonds, but lots of applications actually don't need a bulk diamond, but rather thin layers or individual color centers. So for layered growth, typically what we work with is something like few hundreds of nanometers up to several microns. And here, what you actually see is that this is also done in this machine that I've shown in the first slides, where you actually can take the sample out of the machine. So here you see that we can achieve 500 nanometer thick layers that contain nitrogen. This is a SIMS profile that shows first the nitrogen in blue that is incorporated, and in red you see actually 13C concentration. This is an advantage that you have if you're doing growth. You can also control the amount of nuclear spins by using a methane that is isotopically enriched, but I will come a bit later onto that. Again, you have the concentration of your P1 center determines the characteristics, or should determine the characteristics of your diamond. If coherence times, like here the effective spin dephasing which is here with 6.3 microseconds, if something like this is below the theoretical prediction, you can you probably have incorporated additional defects, spin defects in your crystal. But what you see in this plot here is also that with these layers that we produce, we reach these theoretical limits. And in addition, with this isotopical purification, we reach effective spin dephasing times of up to 6.3 microseconds at the moment. If you go for non-isotopically enriched diamonds, the maximum you can achieve is around 1 microsecond. Why is this of importance? The T2 start time actually is, maybe I can go back to this slide here. The T2 start time also influences the full width at half max of this dip. And with that, it directly influences the sensitivity in magnetic field measurements. So this is very important. That's also why at the moment there is a lot of work going into tuning these properties to the specific applications. Ideally, you don't want to have these P1 centers. They should be as low as possible. They are just needed basically to keep the diamond, the NV center stable in its NV minus state. An ideal diamond wouldn't contain these because it also adds to the decoherence. Another thing that we have with layers is we can add an additional capping on top. And yeah, as you've seen, for the bulk substrates, we can also do this for layers. 10 to 20% of P1 can be converted to NV centers by additional electron irradiation and annealing treatments. But then there is one important thing that is also possible with growth, and this is that you actually can orient the NV center. So the NV center can be located in 4 directions in the diamond, given its cubic crystal lattice, and depending on the orientation of your original crystal, you can get a preferential orientation of these NV centers in certain 1-1-1 directions. And if you use a 1-1-1 oriented diamond crystal, you may even achieve almost 100% alignment of NV centers that are formed by growth in the surface, normal being one of the being the 1-1-1 directions pointing upwards in this case. So it has been shown in recent publications also that this is possible for 1-1-3 and 1-1-0, but the highest orientation is achieved with these 1-1-1 diamonds, and that's something we also do. And this is visible here. So this is an 1-1-1 diamond layer, and this is the ODMR signal where you only get these 2 dips originating from these MS plus and MS minus 1 states that are related to the 1-1-1 direction that is along the surface normal of the 1-1-1 diamond. Again, I've shown you already that that the amount of nuclear spins can be controlled. But what is also possible is that you actually can not only produce diamonds that almost contain no 13C nuclear spins, but also something in between. And this is of importance if you think about computing applications where you actually make use of the nuclear spins in the surroundings. So you can control your spin bath very nicely using this growth approach. And into these layers, you can then also use, for example, if you require single NV centers, you can also go ahead and do implantation again, or try to produce them by growth in this layer. So we are able to achieve here very, very nice, sharp interface layers with our system, and thicknesses down to tens of nanometers actually. So this is a bit larger here for actually measurement purposes, but the lowest we can go at the moment is in the range of 10 nanometers for an intrinsic layer. For a nitrogen doped layer, it's a bit different because nitrogen doping actually increases the growth rate, which makes it a bit more difficult to reach very thin layers, being single-digit nanometers, but we can actually achieve something like 20 to 30 nanometers here, depending also a bit on the concentration that we add. So this is another thing that we develop in this machine that allows us to interrupt the growth. These are delta doped layers that in the end contain single NV centers and also control the surrounding environment using isotopically enriched gases. So what you actually see here in blue is again the nitrogen concentration. We can even tailor our process in a way that only very close to the interface of this layer, we include the biggest amount of nitrogen, but we can also control it in a way that it's homogeneously distributed in this thin layer, as good as you can probably measure it using SIMS measurements. But what you see here is actually just a 5 nanometer layer on the very top of the diamond substrate. So these are the layers that we use, and where do they come into play? If we think about these bulk diamonds, they are especially useful when you use the whole area of the diamond. And this is done if you're not measuring the magnetic field, but you turn around this principle. So we're going back to this structure here. So if you apply a magnetic field, the ms plus minus 1 state splits up, but and then you can use a microwave to drive it into the specific states. But you can also do a different thing and apply a gradient magnetic field. That gives you actually a sensor for certain microwave frequencies and allows you to detect RF signals. So this is also of interest to people that want to interfere with radar signals. That's why it's also of interest nowadays in defense applications. But what we used it for, and let's see if I can get this to work without. What we here, how we demonstrated its capabilities is actually, unfortunately, that doesn't seem to work. But you actually see this here. This is a signal of a communication between two smartphones that are connected via Bluetooth. So you see the frequency hopping of these Bluetooth signals that is happening. And you can do this in real time, so you can actually track the signals in real time using this diamond chip. So this uses bulk diamond mainly, can also make use of layers that are several micrometers thick, but in most cases a bulk diamond is used. If we go for thinner layers, then and I've heard that you already got a presentation last year in December from Dominic Bucher's group. We're working also with them on getting NMR techniques making use of NMR techniques based on diamond. So you can actually use this sensor to do NMR, conventional NMR, but also you can use this possibility to manipulate your system to transfer the polarization from the NV centers into a liquid, and by that polarize this liquid. And this is shown here. So you have an NMR signal or an MRI signal, for example, that is based on the thermal polarization in blue here. And you can hyperpolarize, so you transfer polarization from the NV to, for example, a 13C spin in a surrounding liquid. And with that, you drastically increase the signal, making it easier to detect it. And especially in MRI, it can even allow you to get information on the species that is detected. So it allows you maybe even to detect metabolic products in an MRI scan. So this is where especially very thin layers and maybe structured layers come into play. So you need a large surface area to transfer as much polarization to the liquid as possible. Another straightforward approach is just using this magnetic field sensitivity to sense magnetic fields in close proximity to NV centers. And for that, we use these nanometer-sized NV doped layers. And what you see here is an ODMR scan that actually contains all 4 orientations of the NV center. And making use of these 4 orientations, you can even get vectorial information of a sample that you measure that is directly put on top. So a standard configuration to measure something like this is shown here on the left-hand side. And basically you have the diamond with the thin layer sample on top, and you use a CMOS camera to detect in parallel on several pixels the luminescence intensity, and with that you can get direct information on the magnetization. So this is actually an image of a floppy disk where you actually see the magnetic domains in this floppy disk resolved by the NMR, by the NV layer on the diamond. And this can be done very accurately, but also in complicated environments. So you can use it also to map magnetic fields in bio samples. So this is a intestine of Drosophila melanogaster. This is a fruit fly actually. And here, this was basically marked using magnetic nanoparticles. And what you see here actually on the right-hand side is the signal of these particles inside this intestine. So you basically have few nanoparticles visible. All of these maps here were taken from one orientation of the NV center. So all of these contain magnetic information, but from a different NV center, and thus gives you an insight in the complete vectorial field of the magnetic field that is imposed by these magnetic nanoparticles. So this is nice for producing layers, but I've shown these the method also for positioning single centers or few centers using implantation. So some of you may think if you're actually planning to use like this a nanometer precise measurement, for example, using the NV being an atomic defect, how can I get NVs into the diamond on a specific nanoscale location? Is this possible via CVD growth? And in principle, yes, that is possible. And that's something we've seen a few years ago, that we can actually do our growth in a way that allows us to specifically dope on certain facets of a diamond microstructure. So what we've seen, or what is also depicted here, is if you have such a pillar structure that is etched and you overgrow this, so here what was done was an overgrowth first with an intrinsic layer, and due to this overgrowth, 111 facets form on the sides here. And adding a short additional growth containing nitrogen, you can specifically dope these 111 facets with NV centers. And in addition to that, you also get the preferential orientation. So this is shown here, depending on where you measure on this small structure. Actually, I'm lacking, unfortunately, the scale bar, but it's shown here. So it's a few micrometer structure. Is that depending on where you measure, you get actually the signal from the NV center and how strong it feels this magnetic field that is applied. So apparently the blue measurement point here sees the highest impact of the magnetic field gradient that is applied, whereas the red is almost there is almost no interaction with the magnetic field. So this again gives you an idea of the full vectorial components of the magnetic field. In addition to that, you can actually make use of this in an inverted way. You can specifically generate defects in diamond, etch them, and this etching leads again to formation of pyramids, but in this case inverted pyramids. And by then growing on this 111 facets on the inverted pyramids, you can accurately place NV centers in these etched pits. You can even produce a smooth surface layer again. And what you see here is actually these positioned NV centers after the growth. And here is a measurement. This was actually done also in the wide field system. That's why it's quite noisy, but you actually still can see, even though this spot is at the size of a micron, a bit smaller, you can see again, even on this very small structure, you get preferential orientation in these grooves. So maybe this is an approach on how to actually place also single centers on a micron, maybe a few hundred nanometer level, but this is at the moment under investigation. Why do you want to place these? So for people that are maybe not familiar with these techniques that use the ultimate resolution that you can achieve, there is one possibility in a scanning probe, microscopy application. So you're basically building a scanning probe that contains a single NV center, and you scan this over your surface. With this single NV center, in principle, you could achieve atomic resolution, having an atomic defect, but as you're a bit far away from the surface, you will lose a bit of resolution, but it was demonstrated that few nanometer resolutions are actually achievable. And how to get these NVs into the tip? Conventionally, you're actually implanting and then producing these tips and check where you in the end up by a statistical approach having a single center. So this is a process that we developed to also to maybe facilitate this. So we've produced such tips in the same way as you've seen before for the pyramids, to produce NV centers specifically on the top facets of the tip. At the moment, this means that these are ensembles of NV centers, so you will lose a bit of resolution, but you end up having a tip that contains the NV centers on every of these tips. So it's not a statistical approach anymore. You actually can define beforehand where you get these NV centers. So I wanna say a few words in the end about quantum computing, which is at the moment on the rise for diamond-based applications, and how this is done. So there are a few companies now in Germany, and one is actually based in Australia that work on diamond-based quantum computing. So using diamond NV center, and at the moment mainly surrounding 13C spins as qubits, and there with that they can achieve quantum computing at room temperature. The problem is that obviously the system is hard to scale. So in principle, there are two approaches to scale, or at the moment there are two approaches studied to scale this system. So what you want is basically that in some way the signal from the NV center is coupled to another NV center. And how can you do that? You can go with dipolar coupling. So you place the NV centers in very close proximity so that they see each other. This was already demonstrated, but you could imagine that placing these in close proximity, which means we're in a range of 10 nanometers, is very difficult technologically, and yeah, it's not something that is straightforward. But yeah, people are working on that. We're also working on that in the European project Spinus and in a German-funded project together with Quantum Brilliance. These NV centers, in principle, may be addressed by a technique that was pioneered by a group in Belgium by Milos Neslatek, using an electrical readout, so photoelectric readout for the magnetic resonance signal, and with that it may be possible to even address these few tens of nanometers spaced NV centers. But again, this is a very challenging approach. A bit easier, maybe a photonically coupled approach, but I come to that on the next slide. Here is actually how we want to achieve it together with Quantum Brilliance and positioning these NV centers. So the approach is using a scanning tunneling microscope to position individual nitrogen atoms, overgrow, and by that actually getting the NV centers in very close proximity. What you see down here is actually the approach that I've shown already before. But this may in the end lead to arrays of NV centers, but this is a work in progress. Another approach is coupling these NV centers photonically. There was a publication by Nemoto that proposed this approach. So you're using an NV center or another color center in an optical resonator device, that is surrounded by nuclear spins. So the nuclear spins again can act as qubits with long coherence time, and by using the photonic emission of these resonators, you can couple them, these resonators, by adequate tuning so that the photons get indistinguishable. Also, this is an approach that is already studied using for quantum communication. So with that, we achieved also in the national funded project the coupling of 2 of these registers containing NV centers. And this was done, I think, over a distance of 20 meters. So you don't need to place them in close proximity. You can, with that approach, couple NV centers on a very long distance. On the other hand, in most cases, it's easier to do this with other color centers, like inversion color centers, as they have a very strong zero phonon line emission. So this makes it easier to actually get the photons indistinguishable. And this is also an approach that is mainly used in our project, but you lose this room temperature operation in that case, because these inversion color centers only have high coherence times if you go to cryo temperatures. We're still higher than what you use in the IBM system, for example. How this looks like in reality is you actually fabricate such photonic crystal resonators shown here, or for example ring resonators that contain NV centers, and these basically the NV center then goes in resonance, or the color center goes in resonance, and you make sure that all the photons that are emitted from your color centers are actually getting out of the resonator, and with that you can couple them. So there is a bit of a technological hurdle here, but this is in principle a bit easier than this dipole approach. So here also lots of our diamond films containing few NV centers are used, and also there's the films that contain lower amounts of 13C to get even higher coherence times. With that, I want to come to the summary. I hope that I gave you an overview on what can be achieved using CVD growth for quantum technologies. Also, for who's not familiar with CVD growth, that you got a bit of an insight in how diamonds are produced. Hopefully you saw that we can produce especially diamonds with high NV concentrations. High coherence times are achievable using this approach, so T2 star values that are well above a microsecond. And one key opportunity that you have is this oriented NV center formation that where you can make use of a single orientation in the end. The local positioning is something we're at the moment working on very strongly, and we hope that in future we can get this done for single centers by growth, having diamonds or diamond NV centers with very good coherence properties, but this is still work in process. But if we succeed, maybe it will be one of the key ingredients for diamond-based quantum computing. So with that, I want to thank you for your attention. Also, I thank the funders and the people from IIF that supported this, or that actually provided lots of the data. Also the groups that are involved in this project, and of course the collaboration partners that we have in these various quantum projects that you see on the right-hand side. And yeah, with that, I'm at the end. And if you have any questions, please ask.
Peter, thank you very much for your amazing presentation. It's really very impressive array of achievements. We are open for questions. Abby, please ask your question. You can raise your hand or just unmute yourself and start asking. So Abby, please.
Olga, are you calling on me?
Yes, please. You.
Yeah, hi Peter. Great talk. Thank you so much for covering everything from the growth to the NV sensing applications. So at the beginning, you were talking about the Secchi growth chambers all the way at the
Yes.
beginning. And for somebody, myself, I've dealt with different material, the CVD diamond, as well as HPHT nanocrystalline diamond. I focus on the surface, but I'm interested in actually looking at doing growth myself. What do you think the bar is to being able to use these particular growth chambers and actually getting, you know, decent results of quantum grade diamond materials for NV sensing?
Yeah. So that depends on what you call decent grade, I would say. So the question is probably what you want in the end. If you want to have high amounts of NV centers, there, especially contaminations that you may get from your gases will not play such a big role. From a growth point of view, I would say that most of the systems can provide you with very good quantum grade diamonds. You may have from time to time the issue that you get incorporation of silicon, having, for example, a silicon dioxide component. But in principle, yeah, most systems are capable of doing that. Then you just need to make sure that your gases are well purified and don't contain too much nitrogen, except if you actually in the end want to end up having a very heavily nitrogen doped diamond. So it depends a bit on your application. If you're focusing on very pure intrinsic diamond that you basically specifically dope on certain precisions or in certain depth, it may be difficult to achieve it with all of these systems. So it's, yeah, I only can give this very general answer.
Very good. So considering the placement of NVs, many people just use a radiation of nitrogen 14 or nitrogen 15 to have, you know, some sort of, you know, delta layer at some sort of depth of 10 nanometers or a micron. But
Yep.
what's your perspective? Because of course, as you highlighted, that ends up damaging the diamond in the surrounding area. So if you could create your perfect growth of nitrogen, which has a lot of active NVs, what was the route that you would pursue?
So yeah, this is basically a bit of a work in progress. I've shown these delta doped layers, and these layers ultimately, as at least that's what I think, ultimately may replace the implantation pathway, because it should end up with better quality, meaning higher coherence times, higher stability, and better controllability. But this very thin growth of especially then individual color centers is, yeah, it's quite delicate. It's difficult to achieve and requires also very long characterization times. So the feedback circle is rather time consuming, and that's why at the moment I cannot really say definitely that it works well, because it may also have some backdraws that we don't foresee at the moment. But in principle, it should be able to replace it ultimately at some point. Because one of the things that you have in diamond is that if you're doing an implantation and you're damaging your crystal lattice, this is known for many other semiconductor materials, even to do doping. Afterwards, you can do an annealing treatment and basically do a thermal healing. This is not really possible for diamonds. So if you generate lots of vacancies, you may get few vacancies also diffusing out, but some of these may generate vacancy clusters that could be charge traps then, or could act as charge traps for the NV centers, which destabilizes them. So my guess would be that if you succeed in getting these thin layers few nanometers with accurate positioning and good coherence properties, it will ultimately replace the implantation.
Sorry, I don't want to monopolize your time, but you were talking about clustering. Have you witnessed a large amount of NV clustering or nitrogen clustering during your work?
So what we see typically for low doped layers is that we get some kind of clustering of the NV centers to some extent, especially if you're having a step flow growth mode for 111, you actually see that the growth proceeds along steps. And at the edge of these steps, you typically see a higher amount of nitrogen being incorporated. So that's or NV centers being incorporated. On the vacancy side, it's very difficult to detect it, but this is this is probably something that causes also destabilization when you do irradiation that generates vacancies. When you use this approach to generate additional vacancies, and you work with a too high dose, you will drive all your NV centers to NV0 state. So the reason why this could happen could be clustering of the vacancies that form then vacancy traps and ultimately some kind of a p-type conductivity, so holes.
Very good. Thank you so much.
Peter, is it, just to continue questions from Abraham, is it proved that there are vacancy clusters are formed, and what is characterization method when it is over radiated with electrons?
So this is so far, I think, not proven. It was shown that vacancy clusters can form, but I think given that typically the concentration is very low, it's difficult to detect it directly. Also, you cannot make use of the NV center directly, for example, to detect these, because the vacancy clusters do not have a spin. So there's no direct interaction except for this maybe charge destabilization. So it's a hypothesis, but it's not yet clear if this works.
And say for your 1 ppm of nitrogen samples, what electron irradiation dose would you recommend in order not to create NV zeros but have some decent fraction of NV minus? Is it 10 in power 17 electron per centimeter squared or even lower? We are going to run some systematic experiments next week, but it would be good to hear.
So this is a good question, and I think all groups have somehow their own recipe for that, but it also highly depends on what you want to use these diamonds for in the end. Because if you're using very high power for your application, so you're basically putting a lot of laser power into the diamond, you will by ionization drive the NVs to an NV0 state if they are unstable. And this is even worse if you already have done irradiation at a too high dose. So I can comment, for example, on these wide field layers that we use that typically contain around 10 to 15 ppm of P1. They're a good irradiation dose that works for our experiment is in this range of 10 to 17, maybe up to 10 to 18 at 1 mega electron volt. This is also of importance. Obviously, if you increase the acceleration voltage, maybe up to 10 MeV, then you need to decrease the dose to some extent. So it's very, very hard to say. There's also a nice publication that describes on how many vacancies are formed depending on acceleration voltage and dose. So maybe this can also help you to make a better decision on what is helpful for your specific application. But generally, you need a lot more vacancies than you actually end up with having NVs. So,
please, more questions from the audience.
Peter, I had a question. Yeah. So, well, two questions that are unrelated. first question was, you mentioned that it's nitrogen accelerates the growth during CVD.
Yeah.
Is it known why mechanistically that happens, or is it just more or less an empirical, well-established fact at this point?
Yeah, that's a good question. Actually, I think there are some theories, but I think it was never directly proven what's the cause behind it. So it may be related to changes in the chemical potential. It may also just be related to changes that occur to the diamond lattice by including nitrogen. Yeah, it's most probably something related to the chemical potential. We've also observed this in case of phosphorus doping. There you also see an increase in growth rate, whereas for boron doping it's the other way around. So if you add a p-type dopant, you actually decrease your growth rate. So in that case, it seems to be very much related with the chemical potential.
Oh, yeah, interesting. And yeah, second question would be, so how do you see these NV CVD grown NV technologies for quantum sensing as compared to silicon carbide based? Because I know it's there's some also interest in the use of silicon carbide with defects for quantum computing or applications. So how do you see diamond as compared to these other platforms?
So as you've seen, the typical size of diamonds is in this millimeter range, and silicon carbide has this big advantage that you get these nowadays, I think even up to 6-inch wafers. I think conventionally you get them at least at 4-inch. So you can produce a lot of devices on such a wafer. So that's a big advantage, the processability in standard cleanroom equipment that is just not there for diamonds. And this is also why, especially in this region for quantum computing, a lot of people work on it at the moment, because it makes these things a lot easier that require lots of technological steps. On the sensing side, so I have to say that for computing, also in silicon carbide, you lose this advantage of having a room temperature or close to room temperature operation. So this means that here diamond has an advantage, but in the end it may not work well because you cannot process it in the clean rooms. For quantum sensing, on the other hand, people for magnetic field sensing especially want to have as high T2 star times, meaning as low full peak width in the ODMR as possible, and that means you in the end need a defect that is not interfering with lots of other spins. And in case of silicon carbide, you typically get coherence times that are significantly lower, which makes it difficult to use them at room temperature for such sensing protocols. So I think in the sensing regime where you typically also don't need you do not always require lots of technological steps, the diamond will in the next years play a bigger role than these other materials.
Oh, great, thank you.
Peter, and maybe a little bit to continue along the road that Nicholas started. So if to compare diamond technology with OPM technology for quantum sensing, which is optically magnetically pumped magnetometer. So
yep.
Based on alkaline metal vapors, right? So there is a difference about 2 orders in sensitivity where OPM beat diamond in this regard. Yep. And it looks like that technology is very well developed and in a very fast commercialization path as compared to diamonds. So looking forward, do you see where diamond magnetometry can compete with OPM, or maybe it's already that niche is occupied by OPM?
So the biggest advantage that OPMs have, from my point of view, is that they have this very low sensitivity, and probably for diamond magnetometer, we may be able to achieve similar sensitivities, but we need to make use of additional techniques. There's also one group at IF working on getting basically a lasing with diamond, and then driving the diamond at the laser threshold. This would significantly increase the sensitivity, but requires quite sophisticated optical equipment to achieve this. There is also work on additional magnetic flux concentrators, for example, to get higher sensitivities. But we will see improvements there. But from my point of view, the biggest advantage that we have in the end with the diamond is this capability of measuring the full magnetic field vector. So having these 4 orientations present all the time, we can measure the vector magnetic field, in contrast to the OPMs that only give you a scalar. So basically, you have this high sensitivity, but maybe you're better off having lower sensitivity, but you're able to measure all orientations of a magnetic field. And thinking about, for example, applications where you want to do, for example, magnetic navigation. So this is something also that is discussed a lot at the moment. So GPS-free navigation systems. If you can map the full magnetic field and detect the full vector magnetic field, you may be able to navigate a lot more accurate, even though you don't have this very high sensitivity. So the vector magnetic field measurement, and in addition, this calibration-free approach is very helpful. And maybe the bigger advantage, and yeah, does not require this ultimate sensitivity in the end.
Peter, do you know in this regard if there are already commercial application of vector magnetometers based on diamond? Because it's already for 5 years at least, say, being discussed, and it's long enough period of time to commercialize something, but I did not hear that there are some commercial devices. I don't know if you know.
So I'm not aware of a commercial device that is for sale. I'm aware that several RTOs in Europe have a vector magnetometer based on diamond that they employ for example, for these mappings. And I'm aware of the company Bosch in Germany that actually builds magnetometers based on diamond. But again, this is at the moment not a product, but that you can buy, but they already demonstrated this in a module, in a miniaturized module. And I'm quite sure that we will see rather soon some products in the market. So one of the issues that probably people are facing is that having these small diamond substrates and doing overgrowth on these small substrates always produces in the end some variations in your characteristics. So you don't have this chance to use, for example, as you would have it for other materials, where you have in the end a large wafer where you can take individual elements for your sensor out that are all behaving the same way. This is something that you typically don't have with diamond. So all of these grown layers, depending on the substrate, may behave differently. So this is also a thing that is very difficult for commercialization on a large scale. So on an individual scale, we see these, but for a commercial product, I think this may also be a reason that we just don't have the amount of diamond volume that is necessary for large commercialization.
Okay, thank you so much. Please, if anybody else have questions, please feel free to ask. I don't see any raised hands.
One more,
Maybe
Olga.
Abraham, please, your question.
Peter, you're talking about the vector magnetometry. Can you please go back to that pyramidal structure in your talk that shows the oriented NVs, please?
This one,
Right
yeah.
there. Yes. Lovely slide. Now, is it true that on each side of your pyramid, those are 111 terminated diamond facets?
Yes.
Okay. Have you been doing any post-growth chemistry or any post-growth processing to increase the spin coherence times of those NVs in those 4 different unique orientations?
No, at the moment not. In this publication in PSS, you actually find the coherence times.
Mm-hmm.
So this is the top one here.
Okay.
And they are, at least on what we expect to be in terms of P1 concentrations, what we expect, they are at the limit of what could be achieved. So one thing to mention here is that obviously as these NVs are formed directly during the growth, the amount of NVs is not as high as if you're doing an additional irradiation or annealing treatment. If you do this on this pyramid, you will lose the preferential orientation, because then the vacancies will diffuse in all orientations. So that's a thing to mention. For this oriented growth, you have to live with the typically ppb range of NV centers that are already that are grown in during the CVD process.
Very good. Well understood. But in consideration of doing any overgrowth, that's something that you guys have not readily explored. Now, is this purely done in-house? Is there any way to have samples like this exported?
Sure. So as Fraunhofer, we always can provide sample based on some development contracts that we do, and we can also from time to time, depending on if there is a direct cooperation, maybe already, we can also provide these samples for test purposes. So this could be possible. So just maybe if you're interested, send me an email and we can figure out what you actually need, and if we have these samples available that you actually need.
That's great. Yeah, I sent you an email about the clustering already, so I'll follow up and we can stay in communication. Thank you so much.
Great. Thanks.
Oh, Messias, please, your question.
Peter, very nice talk. My question is with reference to this old problem of growth rate enhancement by nitrogen. You mentioned that it's probably due to chemical potential effects, so boron decreasing the growth rate and nitrogen and phosphorus increasing it. For nitrogen, you have an increasement by up to a factor of 10. How big is your experience with the effect for phosphorus and boron?
So for boron, I think what we observed is that as soon as you add boron, you get a decrease by maybe, it goes down to a fifth of the original growth rate, more or less, as soon as you, like if you start with something like a micron, you end up with being in 200 nanometers per hour. For it's difficult to say. Normally we work for boron, as the incorporation efficiency is so high, I think the variation is very low in the gas concentration you typically have. So as soon as we add boron, we are in this range of maybe 200, 300 nanometers per hour. Obviously, this also depends again on some parameters like the methane concentration, but it goes down by this value approximately. So it's not as strong as for nitrogen, but as you know, for nitrogen, if you want to get really 10 micrometers per hour, you add quite a lot of nitrogen also in that case. So for phosphorus, this is even more difficult to answer, because there sometimes you're facing the problem that your phosphorus precursor gas contains nitrogen, so it's not easily you cannot easily discriminate if the enhancement comes from phosphorus or from the nitrogen. But what we've seen, if we use very pure phosphine gas, is the phosphorus, the improvement is on a similar level as for nitrogen incorporation. And for phosphorus, what we also saw is that there may be a stabilization of the 110 facet ultimately. On 111, for nitrogen dope, you typically see a stabilization of the 100 facet, but for phosphorus, it seems like the 110 facet may be stabilized. So there is a difference in between these, the enhancement of the growth.
If you talk about stabilization, so you say that the growth velocity is in this direction?
No, it's not in this direction, but in the others. So if you end up having lots of, for example, this pyramid for phosphorus dope growth may end up having facets that have a 110 plane. So that means actually that this plane is more limiting for your growth. Whereas if you add nitrogen, here the 100 plane is the limiting plane. So the growth direction should be more along other directions than 100.
Mm-hmm.
So yeah, this is what we observe on 100 substrate.
Okay. Thank you very much.
So I would like to thank our speaker again on everybody's behalf. Peter, have a great 2025, exciting research findings, and continue to advance diamond field. Okay,
Yeah.
bye.
Thanks.
Thank you. Bye.